Hi guys, today we're going to be focusing on a technique called nodal analysis. So we're going to be looking at this circuit here. This circuit has resistors, has independent current sources, and a dependent voltage source here. So basically, nodal analysis, you want to find and calculate the voltage in each of the nodes in the circuit. So for example, if we have a resistor here and current going into the positive terminal of the resistor, we could say by Ohm's law, the current is equal to the voltage drop in the resistor divided by the resistance, which is equal to VA minus VB divided by R. So using this kind of technique, we're able to perform KCL in each of the nodes and solve for the voltages in each of the nodes. So let's look at this circuit here. We're going to put the ground here, which is 0 volts. This ground will be connected to these bottom nodes here. It's the same node. So this will be 0, 0, 0, and 0. We'll say this is node 1. This is also node 1, and this is node 1 as well. We'll say this over here is node 2, this is 2, and we'll say this is node 3. So performing KCL in node 1, what we could say is the current going in is equal to the current going out of the node. So let's say this is I1, right? And we'll say that this current here is I2. So by performing KCL in node 1, we'll say the current going in, say 8 milliamps, plus I2 equals the current leaving, which is I1, and 2 milliamps is leaving too. Plus 2 times 10 to the negative 3. Now I1 is just equal to the voltage of node 1 minus the voltage of node 0. But node 0 is grounded, so that's 0. So we'll say V1 minus 0 divided by the resistance, which is 3000, is equal to V1 divided by 3000. Okay, so basically we're not going to simplify this yet. We're just going to look at each of the nodes and each of the currents, and then we'll go ahead and simplify. Next, let's look at node 2. So node 2 is over here. We'll say the current going in equals the current leaving. So we'll say this is I3 here. So the current going in, which is 2 milliamps, so 2 times 10 to the negative 3, equals the current leaving. So IS is leaving from 2 to 3, and I3 is leaving from 2 to the ground. So we'll say IS plus I3. I3 is again equal to the voltage in 2 minus the voltage in the ground, which is 0. So we'll say V2 minus 0 divided by the resistance, which is 1 kilo ohm. And we know, oops, sorry, this is 3. And we know that IS, which is over here, is the voltage in 2 minus the voltage of 3 divided by the resistance, which is 2 kilo ohms. Okay, so now let's look at 3. So node 3, we'll put this as over here. We'll put this as I4. So in I3 we could do KCL. Sorry, node 3 we could do KCL again. So the current going in, which is I3, IS, equals the current leaving, which is I2 plus I4. We know IS, which we calculated, is V2 minus V3 over 2000. And we know I2 is in this was defined in this equation here. We actually don't know what I2 is actually. We know that I2 shows up in the analysis of node 1. I4 is equal to the voltage in node 3, so V3, minus the voltage of the ground, which is 0, divided by the resistance, which is 6,000 ohms, which is V3 divided by 6,000. Okay, so basically we have almost everything, or we did the analysis of these 3 nodes, but now we know that this is a dependent voltage source. And the dependent voltage source, we could find an equation for that as well. So if we do if we look at this dependent voltage source, we could say V1 minus V3 is equal to, this describes the voltage drop, 4000 IS, but we know what IS is from this equation here, which is V2 minus V3 divided by the resistance, 2K. So we could say V1 minus V3 equals 4000 IS, V2 minus V3 divided by 2000. Okay, so we could simplify this a little further, and we'll say this simplifies to V1 minus 2V2 plus V3 equals 0. So now we have an equation with 3 unknowns. We need 3 equations that are linearly independent in order to solve an equation with 3 unknowns. So we'll label this as equation A. Okay, so now let's look at node 1 again. Let's simplify this a little further. So we have 8 times 10 to the negative 3 plus I2 equals I1, which is, I1 is equal to V1 divided by 3000 plus 2 times 10 to the negative 3. Now let's simplify this a little more. We'll say that I2 is equal to V1 divided by 3000 minus 6 times 10 to the negative 3. We don't know what I2 is, but we know that I2 shows up in node 3. So let's look at node 3 and let's isolate for I2. So we know what IS is. IS is just V2 minus V3 over 2000 equals I2 plus I4, which is V3 over 6,000. We could simplify this further, and we could say I2 is equal to we'll bring V3 over to the other side. It's equal to V2 over 2000 plus V3, minus V3, 1 over 2000 plus 1 over 6000. Okay, so now we could say, okay, well these I2s, they're equal. We could set this side of the equation equal to this side of the equation and simplify even further. So let's do that. So we have V1 over 3000 minus 6 times 10 to the negative 3 equals V2 over 2000 minus V3, 1 over 2000 plus 1 over 6000. If we simplify this further, we'll end up with an equation where V1 times 3.33 times 10 to the negative 4 minus 5 times 10 to the negative 4 V2 plus 6.67 times 10 to the negative 4 V3, and this equals 6 times 10 to the negative 3. So now we have equation B. We have equation A, we have equation B that depend on these three unknowns, V1, V2, and V3. Now we need equation C, a third linearly independent equation in order to solve for this problem. So let's look back at node 2. Node 2, we could simplify even further. We could say 2 times 10 to the negative 3 equals IS, which is V2 over 1000. I3 plus IS, which is V2 minus V3 over 2000. This simplifies even further to 2 times 10 to the negative 3 equals 1.5 times 10 to the negative 3 V2 minus 5 times 10 to the negative 4 V3. So now we have equation C. So we have equation A, equation B, equation C with three unknowns. So we have three equations, three unknowns, and we're able to solve for the nodes now. So let's do that. We could actually put this into a matrix. So let's do that just for simplification. So we have 1, negative 2, 1, so that's equation A. Then we'll do this, V1, V2, V3 equals 0. And then here we have 3.33 times 10 to the negative 4, negative 5 times 10 to the negative 4, and 6.67 times 10 to the negative 4. The bottom, and then it's equal to 6 times 10 to the negative 3. The bottom equation, we have 0 for V1, but we have 1.5 times 10 to the negative 3, and negative 5 times 10 to the negative 4 equal to 2 times 10 to the negative 3. So we have three equations and three unknowns. We're actually able to solve this using the Gauss elimination method, but we actually could solve it on the calculator. So if we hit mode 3 times, we click equation, and we hit 3 unknowns, we're actually able to solve this. And we have to put it in this format. So you'll get a prompt where it says A, B, and C, and then D is actually on the other side of the equal sign, and you could solve for where there's no variable here. So actually, if you put this in the calculator, you end up with V1 is equal to negative 2.28 volts, V2 is equal to 6.28 volts, and V3 is equal to 14.86 volts. For this equation, we want to solve what V naught is. V naught is actually just V2 minus the ground, which is actually V2. So V2 is equal to V naught, and V naught is equal to 6.28 volts. So this is just a simple analysis of finding the nodes in a circuit that looks like this. using nodal analysis. Nodal analysis uses KCL, and we're able to find the voltage of each node by doing that. Awesome, thank you.